Describing function analysis. We start with the van der Pol oscillator, which is this differential equation. We assume that this equation has a limit cycle oscillation, and this oscillation signal is of this type, is sinusoidal, a sin omega t type. The feedback system we build for this nonlinear system has a linear block. Even though it's unstable, we assume that it has low pass properties. So if we bring the x dot x squared to the right side of this equation, the part remaining on the left hand side is a linear ordinary differential equation. The right hand side quantity is nonlinear. The RHS quantity now becomes x dot x squared with a negative sign, and the left hand side quantity is x double dot minus alpha x dot plus x. So basically this means that the linear part is being forced by the nonlinear part, which is on the right hand side now. So the linear block can be thought to be receiving an input from the nonlinear part. So with this idea, we construct this block diagram. So x dot x squared with a negative sign is the nonlinear part. That's giving an input to the linear part. And what comes out of the combination of nonlinear and linear is x. And this is the block diagram for the system. So we have assumed that this linear block is having low pass properties, even though it is unstable. Now with those assumptions, we have x dot equals a omega cos omega t, and w turns out to be this quantity, which upon simplification gives me these terms, a cos omega t term and a cos 3 omega t term. And now since the linear block has low pass properties, it's reasonable to assume that the third harmonic is sufficiently attenuated by the linear block, and in effect, it's not present in the signal flow after the linear block. This means that we can approximate W by just the first harmonic only. So with these assumptions, the W becomes this quantity, which in the frequency domain takes this form because the derivative becomes multiplication with omega. So the n a omega contains the everything else and multiplied with negative of x of s in the frequency domain. So with those simplifications, with those assumptions, we have the nonlinear part taking this block, which is called the quasi-linear approximation. So this whole thing is a quasi-linear approximation of the van der Pol oscillator. Now we can write the characteristic equation of the system, because it's now comprising of linear subblocks after those assumptions, and we find that the equation has solution when a is 2 and omega is 1. So that is, the amplitude is 2 and omega equal to 1. So when x is a sin omega t, when a is 2 and omega is 1, a limit cycle oscillation is possible. So in terms of Laplace variable, we get the same conclusion when we obtain the corresponding characteristic equation and solving for its roots, which are the eigenvalues of the linear system. So the eigenvalues work out to be plus or minus j when a is 2. So the limit cycle oscillation has these shapes in the approximate analysis that we are doing here. When alpha tends to 0, we have a limit cycle oscillation which is resembling a circle. When alpha is 1, we have a distorted, closed curve on the plane as a limit cycle. And when alpha is 4, the distortion further increases, but the curve is still closed, which is why it's a limit cycle. Let's talk about the stability of the limit cycle. Stable limit cycles, first figure, are all trajectories in the vicinity of the limit cycle converge to it as t goes to infinity. Look at the inside trajectory and the outside trajectory. The inside trajectory is going towards the limit cycle, so also the outside trajectory. And therefore, this limit cycle is a stable limit cycle. Unstable limit cycle, all trajectories in the vicinity of the limit cycle diverge away from the limit cycle as t goes to infinity. Diagram B contains a unstable limit cycle where the inside trajectories are going away towards the origin, The outside trajectories are also diverging away from the limit cycle. Semi-stable limit cycles are those closed isolated trajectories where some of the trajectories in their vicinity converge to it while the other trajectories diverge from it. So this is an example. The inside trajectories are going away from the limit cycle and the outside trajectories are going towards it. So this is actually a semi-stable limit cycle. An unstable limit cycle is those limit cycles where the inside as well as the outside trajectories diverge away from the limit cycle. In most of the control systems, though, limit cycles are undesirable, and this could happen because of many reasons. Limit cycle, as a way of instability, tends to cause poor control accuracy. The constant oscillation can cause increased wear or even mechanical failure of the control system. Limit cycling also causes other undesirable effects such as passenger discomfort in an aircraft under autopilot. So in order to develop a basic version of the describing function method, the system has to satisfy the following 4 conditions. So these are the assumptions for the describing function method to work. That first assumption is there is only one single nonlinear element. The nonlinear component is time invariant. Corresponding to a sinusoidal input, only the fundamental component in the output has to be considered. The nonlinearity is odd in nature. So with these 4 assumptions, we can build a describing function approach for nonlinear systems. In this example, the plant is linear and the controller is also linear. However, the actuator involves a hard nonlinearity. So this system can be arranged into a figure of this type, 5 point for this figure, by applying the assumptions that we just discussed. The actuator's nonlinearity is here. So the nonlinear element is actually the actuator, which is having some kind of a play, which could be causing this nonlinearity. So with the assumptions made, we have a describing function coming here and a linear block here. So under those assumptions, it is possible to apply and write our system in this form. A hard nonlinearity is one whose discontinuous nature does not allow linear approximation. Example is a Coulombic friction, a backlash, hysteresis, dead zone, saturation, and so on. Let's look at the Fourier series analysis. If Wt is conformable to Fourier series, then it is possible to expand it in terms of harmonic functions like this. It's an infinite series. So there are theorems in Fourier analysis which give the necessary and sufficient condition for the series of this type to converge. That theory also gives us the way to compute these coefficients of this infinite series. A0 must be this integral, an and bn must be these 2 integrals. So due to the 4th assumption above, A0 has to be 0. So we assume the nonlinearity to be odd. So that's causing the A0 component to be 0. The 3rd assumption implies that we need only consider the fundamental component W1T because the higher harmonics are assumed to be not having much influence on the dynamics of our system. So with those assumptions applying, so the Wt, which is approximately W1T, is this quantity here, which may be expressed in the mod amp form, and it takes this shape, m sine omega t plus phi, where m and phi may be computed from A1 and B1, and they work out to be these 2 quantities. Square root of A1 squared plus B1 squared, and phi A omega is arctan of A1 by B1. So we now give the definition of the describing function. The describing function of a nonlinear element is the complex ratio of the fundamental component of the nonlinear element and the input sinusoid. So the ratio of these two quantities, which is 1 over 8 times B1 plus JA1, this quantity is the described